No, thanks to you for organizing this conference this school actually, that I'm really looking forward. So thanks to the organizers who are here and to those who will come or are here in spirit, let's say. So for those who I haven't met yet, so my name is Valentina and I come from a laboratory that is in the south of Paris, which is called the LPTMS. And I will keep you company in the first 2 mornings, so this morning and tomorrow morning. And I'd like to tell you something about this topic, which is high-dimensional random landscapes. So I will go to the blackboard in a minute. I just have a couple of slides that are a bit of an introduction. And also I wanted to advertise that there are some notes. So these are handwritten notes, but maybe they are useful to follow. And there are much more details in there than what I'm going to tell you at the blackboard. Okay, so what is the topic? So I think, well, the title is self-explanatory in some sense. So what I'd like to tell you about are problems related to landscapes, which are simply functions that are high-dimensional. So these are functions which, as you will see, depend on very many parameters, and they are random. So the idea is that you associate to all of these parameters which describe the state of your system, you associate a value of this function, and this function has some probability distribution, and you want to characterize statistically what happens to these landscapes. Now, why do you do this? So this type of problems emerge in general when you want to describe physics or properties of complex systems, and in particular, in general dynamics of complex systems. So the idea is that these are systems where you have very many degrees of freedom, they all interact with each other, and they have a time evolution, and you want to somehow describe the time evolution as some effective optimization process. So the idea is that the system evolves trying to optimize some function, which could be an energy or a fitness or a cost function. And this function is high-dimensional because the system itself contains many degrees of freedom. And you introduce randomness to model, let's say, the complexity of the interactions. So the idea is that all these degrees of freedom interact, and the couplings that describe these interactions can be very heterogeneous, very fluctuating, and so you think that it is a good idea to describe them introducing random variables, and therefore you introduce families of models that you want to characterize statistically. So this is the picture. The time evolution is trying to optimize such a landscape, and the question is, can you understand something about this evolution looking at the structure of this landscape? Now, just to make some sort of introduction of and give you some examples of where these problems come out, I wanted just to mention a few papers so this is not a list that is, let's say, exhaustive in any sense, but these are papers that are written by some people that you will see around in these 2 weeks of the school, so maybe you can also talk to them. So these are just, I will go very fast through this. So there are some examples which come out naturally when you think about problems of artificial neural networks that you will hear about. So this is an example of models of, if you want, memories in high dimension, where you try to build your landscape in such a way that the minima of the landscape are very close to some specific configuration that you want to store. Then on somehow, so this is a so-called Hopfield model, or variations of it. You have also landscapes which emerge in artificial neural networks. This is an example of restricting Boltzmann machines, where you have some sort of effective Boltzmann-Gibbs distribution with some energy that depends on many parameters, and some of these are random variables. You have examples more generally on biology, soft matter, and ecology that you will also hear about in some other lectures. So this is a toy model of high-dimensional tissues. So this is related to constraint satisfaction problems in high dimension, and it has interesting features of the landscape that maybe go beyond also the example of tissues. This is an example of the so-called Lotka-Volterra equation. So this describes the evolution of, let's say, large ecosystems with very many species which can coexist. And in this case, if you choose your coupling appropriately, you can also interpret this time evolution as the optimization of some effective energy landscapes. So there will be lectures of Guy Boonin on this in the following days. This is a quantum slide, if you want. So the idea of this works is you can think, okay, in general, you think about classical systems when you have these landscapes and classical dynamics, but you may also imagine that you have such a complicated random function, and you think about optimizing it with quantum algorithms, for example, quantum simulated annealing. And here you have basically the same question, so how much of the features of your energy matter, and what is the hope for the performances of your optimization? This is an example of a paper motivated by these questions. You can also ask, okay, take these complicated landscapes as some sort of classical potential, and then I look at quantum unitary dynamics on top of this landscape. What happens in that case? So this is a further example. And then these, let's say, last examples are actually very much connected to what I'm going to tell you in a minute. So this is a problem of inference in high dimension, and what I'd like to do next is to take such inference problem as a motivation to introduce the landscape problem. So you see that the keyword here is denoising. So the idea is that you have problems where you make some measurements which are somehow affected by noise, and you want to reduce the noise and recover information about what you're measuring. And the type of models that emerge in these settings are actually very close to models that people have been studied a lot since years as models of glasses, so of interacting particles, and this is an example, and they have an interesting dynamics, and there are many landscape questions that you can ask as well on these problems. Okay, so this was very fast, but just to give you somehow some ideas. So what do you want to do then? Well, the idea is you want to say something, as I was saying, about the structure of your landscape. So basically, is your landscape kind of smooth, or is it very complicated, very non-convex, very rugged, like in this picture? And the techniques that you can use to try to do this are standard tools of statistical physics of disorder systems. So I will mention a lot random matrix theory here, large N calculations, saddle points, large deviations, which I will not discuss much, but it's also connected to this, and then a replica trick and formulas to count things that are nowadays called Cut-Rice formulas. Okay, now these two pictures are somehow two different situations which correspond more or less to what I'd like to discuss here. So it's essentially split in two parts. I thought it would be nice to start from examples of landscapes which in some sense are easier, and this is the case of quadratic functions, because these are problems that you can really address using random matrix theory, so I will use this as an excuse to revive and to recall some notions of random matrix theory. And then I hope I will handle time well, and then we can go to more complicated problems, which are more glassy in some sense. Okay, so I'll go now to the Blackboard. This is an apology in advance. So to save some time, I will not. I decided not to write down references at the Blackboard. But there are very important references here. In particular, the first part is very well established, so there are papers which are worth to look at, and you find them in the notes, hopefully, all the relevant ones, so please check there. And I'll also try to not to use a notation that is too heavy, so to write what is a matrix with a hat or a vector with a sign, which means that maybe something will not be clear, so please, if it is not clear, just stop me, and this is an invitation to everybody, so if you have comments, questions, or you want to add anything, please go on and stop me. Okay, so unless there are questions here, I should now try to do the switch. Okay, and really stop me. I mean, I also tend to speed up at some point, so this is not good, so feel free to interrupt. Okay, so this is part one. quadratic landscapes. And I'd like to tell you first a motivation to introduce the problem. So this is one specific class of problems which are related to inference and denoising. And I call this an easy inference problem, and easy will have a specific meaning that I hope will be clear in the following. And the idea here is to look at the problem of denoising. So once again, what is denoising? So the idea is that you have some object that you're measuring, and this object contains some information that you want to retrieve. So this information is usually called a signal, plus some noisy fluctuations on top. And what you ask is, if I do these measurements many times and I look at some statistics, can I somehow average out the effect of the noise and recover information on this underlying signal? So the specific problem I wanted to look at in here is a problem of denoising of matrices, large matrices. So you have a matrix M, which is what you observe. And you know that this matrix contains some signals. So now I'm writing down some specific form of my signal. So I put a coupling here. And then, so let me assume that this matrix has components ij. And I have a vector v with components I and j. And then I add another term, which is another matrix ij. And these are all matrices which have size n by n. And n is assumed to be large. Now, this quantity is what you call the signal. And this is what you call the noise, or I will call it also the randomness. Is this big enough to read? OK. OK, so what is the signal? So the signal is a vector, v with n components. And it is, of course, a vector which is unknown. You want to find it. It's fixed, so it's deterministic. And you don't know much about this vector, but you know one thing in this example, which is that this vector is normalized to n. So if you look at the norm, square this is equal to n. So this means that you have a configuration space, which is a huge sphere, which here is in 3D, but actually you have to imagine it in dimension n. So let me call it as n. This sphere has a radius square root of n, and your signal will be somewhere on the surface of this sphere. So let's say I put it on the North Pole so that I can call it the North Pole in the following. OK, so this is what you want to find. So the question is, I give you the sphere. Can you say something about the position of this signal on the sphere? And what makes the problem complicated is the fact that you're adding this noise, which is random. So this noise J is a matrix which is symmetric. It is random, so the entries are random variables, and it is Gaussian. So the simplest case is that you take all the entries to be independent up to this symmetry. So IID means independent, identically distributed. Not really identically, actually. So let's say independent entries with Gaussian statistics. So Gaussian means that to write down the probability, I have to tell you the first two moments of these random variables. So you choose, for example, that the average is 0 of all these entries, and you choose a variance that I will call sigma. So the variance of each entry is sigma squared divided by n, and then I put a factor of 2 for the entries which are diagonal. So if you have this information, then you can, in this case, you can write down what is the probability of, let's say, observing one instance of this matrix J. So this will be, since all the entries are independent, this will be the product of Gaussians for all such entries. And if you combine a little bit all the Gaussian weights, you see that this you can write this as some normalization. And then you have a Gaussian term that you can cast in the following way. So this will be exponential of, in this notation, this is becoming small, I guess, minus n divided by 4 sigma square. And then the coupling, you can write them as the trace of the matrix square, where the trace is the sum of diagonal elements of the matrix. And then you have delta jij for all ij's which are, let's say, in the diagonal and in the upper triangle of your matrix. Okay, so this is a very nice ensemble of matrices to work with, because these are matrices which are so-called belonging to the so-called Gaussian orthogonal ensemble, or GOE. So they are Gaussian because they are Gaussian in their statistics. And this orthogonal here is telling you that there is some symmetry property in this probability density, which is a symmetry with respect to rotations of your matrix. So in a sense, statistically, the matrices that describe the noise here are rotational invariant. And this simply means that if I give you a rotation, which is a matrix n by n, like my matrix J, which is real and symmetric, and which is characterized by the fact that the inverse of this matrix is equal to the transpose. This is what characterizes rotations. And then I ask you, well, I give you one instance of the matrix, J, and I give you the rotated matrix, which I call JR, which is simply you mean this? Yes, okay. The important thing is that you have, let's say, this property for what I'm going to say. No, good. Please, any comment is. So let's take, let's say, such a matrix. Let's take the rotation. And what I mean when I say that the statistics is invariant is simply that this rotated matrix, or as people say, is equivalent to the original one, which essentially means that if you look at the distribution, at the probability to observe the rotated matrix, you plug it here, you would have OJ, O transposed, and you see that if you put it inside this trace, using the properties of the trace and this property here, you get back the probability of the original matrix. So this already tells you something about this class of matrices. Okay, I will not write down this. Why? Because it tells you that these two matrices are in some sense equiprobable. And these two matrices share some things. So first of all, the eigenvalues. So what happens to the eigenvalues if I rotate? Nothing, right? So the eigenvalues are the same. So you expect that the distribution will be a function of these eigenvalues. What happens with the eigenvectors? So if I rotate, then the eigenvectors will change, will be rotated. So if U is an eigenvector, which I will write like this, of J, then UR, which is the rotation of U, will be an eigenvector of JR. And I'm kind of telling you that if I take the whole set of eigenvectors of J, and then I take some rotation extracted, let's say, uniformly from the ensemble of matrices which satisfy this condition, and I rotate all my set of eigenvectors, I get something that is equiprobable to the original thing. So in some sense, intuitively, this is already telling you that the eigenvectors themselves are, you can think of them as being some sort of vectors which you extract uniformly on the sphere. Now here you usually normalize them not to n but to 1. So the idea is that the set of eigenvectors statistically of this ensemble of matrices, you can think of them as being vectors that you sample uniformly on the sphere of a given radius 1. So if you think about averaging over eigenvectors, you can, let's say in your mind, replace this average with a uniform average, where the only condition that you impose is that this eigenvector is normalized, but apart from that, it is extracted uniformly from a sphere of a given radius. And this idea will come out, let's say, several times in the following. So I will write it down sloppily, but just to statistically are like, let's say, random uniform on the sphere. Is this okay? Okay. Okay, now this is your problem. So I'm giving you M, and you want to understand something about V. And now what I'm going to do is to rewrite this as some problem of optimization of some landscape. And the way one can do this is by, so if you follow this, let's say, inference path, you can think about what could be good estimators, so good quantities that are in some sense guesses for your unknown signal. And one path that you can choose is to look at the so-called maximum likelihood estimator. So I will just, you can think of this as a guess that you can make on your signal, given that you observe the matrix M. And formally this, I will call it SGS. And this will be the object which maximizes something. So this will be, so you know that your vector V lives on the sphere of radius square root of n, so you want that S, which is the guess of your signal, will also live on the same space. So I maximize on the space of vectors whose norm square is equal to n. And then what I maximize is simply the, this is a G, the quadratic form. So I have my vector S dot ms, where M is the matrix that you are observing. Okay. It's coming in a minute. Who is asking? Ah, okay, Joseph. Ground state. Okay, why ground state? No, first of all, one should maybe motivate why one looks at this form. So the idea is that, well, this comes from an inference framework. So one very fast way to see this is, okay, let's think about probabilities. So let's say that the information that I have is M, and I also know that M can be decomposed in this way, and I know that this is Gaussian. I don't know V, but I know this structure. So if I'm giving M, I can ask, what is the probability that my vector V takes a given value, so let me call it S, given that I observe M? What is this? This is a real number, and I forgot to tell how people call it. So if you take, so you see, you have this term, which is proportional to R, and the fluctuations of this term are proportional to sigma. So R over sigma is just a number that will be the tuning parameter in the following, and it is what you call signal-to-noise ratio. So thanks. And I'll take it positive in the following, just to be consistent. Okay, so we were here. So this is a conditional probability. You say, what is the probability that my vector V, that I don't know, takes the value S, given that I observe M? Now, this probability, I can rewrite it by switching basically the order of this conditioning. So this is like the probability that I have M, given that my V is equal to S, times the probability, or any, if you want, distribution which encodes any information that I have on S in here, and then I have to normalize by P of M. Now, in this inference setting, so this is an object that you call usually posterior, this is what you call prior, and this is the object that you're interested in, that is the so-called likelihood. So this estimator is essentially the object that is optimizing, maximizing this function under the constraint that I'm living on a sphere, and that I know this decomposition here. And this is quite, straightforward to see, so we can do it a sketch. So the idea is you want, so in general you define the log of this quantity. Let me take it as a function of S. And the idea is that I go back here. I know that this is Gaussian and it has this distribution. So that conditional probability, in some sense, I can write it as the Gaussian form, evaluated at M minus this object here, where instead of V, I put the vector S, because I am assuming that V takes the value S. So if you do this and you use that expression for P, you see that this can be rewritten as the log of your normalization that you don't care about. And then you have this exponential here. So this exponential here, you can expand the trace. So this is a sum of all the diagonal elements. So this is n over 4 sigma square. And then I have sum over ij of an object square. And this object is basically, I should put j, but I am assuming that j is m minus this thing here. So let me put it. SISJ. My proportional. Okay, here it should be actually equal. And I'm looking at this as a function of S. So what you can do is you take the log selects the exponent, then you undo, let's say, the square. You will have a term which depends on M, but you don't care about because you are optimizing over S. You have a term which contains the norm of S. So S to the norm S to the power 4. But you're assuming that you are on the sphere, so this is just n squared. And then you have the product between these two, and the product between these two is precisely what I'm writing here. So maximizing this object with this constraint means looking at this at the point which maximizes this quadratic form. Okay. Now the idea is that this is, if you want, already a landscape. So let me rewrite this now in a more clear landscape form. So why do I call it ground state? Because you can see that this SGS is the ground state, so the configuration of minimal energy. Of an I-dimensional landscape, which I will call E of S, where I essentially take this and I put a minus in front. And a factor of 1/2 because it is nicer for calculation. So let me decompose what I know about M. So this will be sum over ij from 1 to n of jij sij, which is the random part, plus the part which comes from V, which I can rewrite as V dot S to the power 2. Okay? And this is defined on the sphere. Okay, so this function has two terms, obviously. So it has a first term, which is coming from the randomness, which defines a landscape with Gaussian statistics. So this is the random term. It's Gaussian. Why? Because the J are Gaussian, and this is a linear combination of Gaussians. So this will have a statistics which is Gaussian. And going a bit back to this idea here, one can see that the statistics of these objects is also in some sense rotational invariant. Not in some sense, it's rotational invariant. So this is, or if you look at one single point, let me call this isotropy. So what's one way to see this? So we have the statistics of J, so we say that J is Gaussian, so this term will be Gaussian. So let's look at the moments of this term. So there will be the first moment, which is easy. So what is it? Yes. And then there is the second moment. So for the second moment, you have to plug in the correlations of the J. So if you do it, you now look at correlations between your random functions. So this is now for r equal to 0. You look at how the landscape is correlated at two different points. You take essentially the product of two of these things, evaluated one at S and the other one at S prime. You take the average, so you will have the average of two couplings. You plug what you know for the average of two couplings, and you realize that this is n over 2, then you have sigma square, and then you have a function that is the dot product of the 2 points divided by n to the power 2. And here you see that, so rotational invariance means that this is an object which is invariant with respect to rotation, it's a scalar product, so the statistics is rotational invariant. And in particular, why people say isotropic, because let's assume that I now want to characterize the statistics only at one point. So I look at these correlations at one single point. So I put S equal to S prime. And what I get is that because I'm normalized, this term becomes equal to 1. So I get something which is totally independent of the particular point that I'm looking at. So wherever I am on the sphere, I have the same fluctuations of my landscape. Okay, this is for the random part, but then you have this other part. So this would be what remains when sigma, which controls the fluctuations of this, is equal to 0. And this is non-random. And I would say that this is, so is this isotropic? It's not isotropic, right? Because you have a special point in here, or a special vector, a special direction, if you want, which is the direction of the sphere, of the signal. So this term is not equivalent, no matter where you are on the sphere, but it knows how close you are to this special point that in my drawing before was the North Pole. So the closer you are to this vector V, the more the energy landscape is biased by this term, and it becomes smaller and smaller. Okay. So if we add these two terms separately, I think we can make, and we go back to this problem. So the idea is we now want to find the ground state. So where is the minimal energy configuration? So if I had only this term or only this term, I could make some guesses for where is this ground state on the sphere. So the easiest guessing is when sigma is equal to 0. So if I kill this term, any guess of what is the ground state? Exactly. So here, SGS is simply my vector V, my signal. If I kill this deterministic term, so I do not bias the landscape in the direction of V. I am in this high-dimensional sphere. Where does one expect the ground state to be? It would be isotropic. So now it means, in some sense, that you don't care particularly about this special direction. Now, this special direction, you are in a very high-dimensional space, so it's only one direction out of n. So do you expect that the ground state would have an overlap in this special direction or not at all? Not at all. So what you expect is that in this limit, you find that your ground state is orthogonal to V, so it will lie in that region that is orthogonal to what I call the signal. For me, the signal is the North Pole, so this region is what you call the equator to be simple. And this is something that is very natural, in particular because you are in high dimensions, so you can do a little calculation and show that, in fact, if you extract two high-dimensional vectors randomly, so you find it in the notes, the typical value of the scalar product is 0. So typically, two vectors in high dimension are orthogonal to each other. And then, of course, you have now the competition between these two terms, and this competition will give rise to transitions in the position of this ground state. And this transition, you can interpret them as in terms of the inference problem, remembering that the ground state is what is supposed to give you information about the signal. Okay. Questions? No? Okay. So now in this way, you have somehow mapped your inference problem into a problem of optimization. You want to find the optimum of that function. And I will use this now to just to summarize some of the questions that you can ask. So 3 questions that for this case of quadratic landscape, you can actually solve quite completely, as we will see using random matrices. Okay, so I leave the landscape there. So let me write down the question. This doesn't work well. Oh. Okay. These are questions and the strategy that are there also for the second part. So let me write them down once. Once for all. So I would say there are 3 type of questions that one can try to answer here. So I give you first a label which is comes from this inference, and then in brackets something which is more for physicists, more natural. So the first question is a question about recovery in the inference setting. And if you think in physics terms, this is a question about, let's say, equilibrium, so Boltzmann measures at 0 temperature. You have an energy, you can define a Boltzmann function, and the Boltzmann function will have a limit beta going to infinity, and the equilibrium state is the ground state, which is what we are looking at. So the question that you ask here is essentially when. So for me, when means for which values of this signal to noise ratio R over sigma. What you're looking for, which is the ground state, in some sense contains relevant information on what you want to find, which is the signal. Of V. And for me, this will mean one thing. So remember, you have the sphere, you have the signal V. We know that in general, vectors which are taken randomly will be very far away from V, will be in this equatorial region. So being informative means that R is large enough so that it's able to somehow pull the ground state and put it somewhere in the direction of V. So somewhere in this drawing in the north hemispheres of this sphere. So let me measure this by this quantity Q, which is simply the overlap between V and the ground state divided by N. So it's this object here, this projection divided by N. And what one wants is that, so you're thinking about the large N limit, so you want that this quantity remains finite when N goes to infinity. So this will have a limit when N goes to infinity, and you want that this limit is not zero, which is telling you this. Okay? Okay, that's one thing, but that's maybe not the only thing you want to know. Because you have a whole landscape, which can be more complicated than just the ground state. So another question that you can ask is about the landscape itself. And this, if you start thinking about dynamics, and I will go back to this in a minute, is related, if you want, to notions like metastability. I think this is really better. Okay, and here what you ask is, essentially, if you have the ground state at the bottom, you want to know what happens at the landscape on top of it. So are there many, and many, I will specify what I mean by many, other minima of your function, which are not the global minima, but which are local minima. And for me, in the following, many means really many. So it means, so you say that there are many local minima when in this large N limit, the number of these local minima is growing, is diverging exponentially with the size of your configuration space. So many means, for instance, something which scales like this when N is large. And if you have many, you can then try to understand what is their energy. So are they close to the ground state in terms of energy? Are they at much higher energy? And also, what is their position with respect to the signal? And the reason why you're interested in this is that the third question that, of course, you want to understand is about, in general, algorithms. or dynamics. So algorithm means, so here you ask, if I am able to find the ground state, so to optimize my landscape, do I recover information out of this procedure? And here the question that you ask is, yes, but how hard is it to find this ground state? So if I run an optimization algorithm, is going to take the age of the universe to find it, or can I do it on reasonable timescales? Now, of course, this depends on the algorithm that you are thinking about, so I will focus here only on let's say, algorithms which are local in space and which are more related to the physical dynamics, so Langevin type dynamics. And the idea is, in some sense, how much time or how hard it is to find this ground state, let's say, with local algorithms, local meaning that they do local moves in this configuration space. For example, Langevin dynamics or gradient descent, which is so Langevin dynamics means dynamics where you start somewhere on your sphere and you want to move, and it's a continuous time dynamics, and you update your configuration, essentially looking at the landscape around you and going always in the direction where the gradient goes down, so the energy goes down. So here you will have minus the gradient of your landscape. And what I mean by this notation is that you have the gradient, but you have to always restrict it to the surface of the sphere. And then you have noise that usually is white noise. So this is gradient descent, and this is noise with the usual, okay, let me write it. These are vectors, so the noise has components because S has components. And you correlate only the same components, and you correlate it only at equal time. So hard can mean, I mean, it's a bit sloppy, defined like this, but for the discussion in the following, I will call hard a situation in which I try to optimize my landscape with this Langevin dynamics in the limit, for instance, t going to 0, which should bring me to the ground state, and I see that the typical timescales that I need to do this are very large, so they are themselves also exponentially large in n. This is what I call hard. And I will call easy situations in which this may scale with n, but as a power. Okay. Okay, now if one looks at these questions, then one realizes that essentially what I'm asking here are questions about special points in this energy landscape. So the ground state is a special point, is my global minimum. Local minima are special points because they are, in fact, minima. So these are all stationary points of my function. And before, okay, let me maybe clarify why these, of course, this is very intuitive, but why these two questions are related? Well, of course, because the idea is that if you have a landscape that is very complicated with a lot of local minima, so you want to reach the configuration that corresponds to the ground state, which is down here. You do it with algorithms that follow the gradient, but let's say, suppose that you start from here. So you may add a little bit of noise to your dynamics, but the idea is that this will follow the gradient. It will bring you down, and you reach this point, and this point is a local minimum. And to go out of this local minimum and reach this configuration, you have to climb up in the energy. There is an energy barrier in here. And with this dynamics, climbing up in energy is complicated because you have the gradient that pulls you down. So you need to use the noise, but if temperature is small, the noise is weak. So this means that it will be, you have to wait for very rare kicks of your noise that are able to send you up here and then find the good minimum. So in general, when you have many local minima with this scaling, you end up with the dynamics of this type, which is hard. So this is very connected, these two questions. Okay, so all of this is about, in fact, understanding essentially how many stationary points you have in your landscape. So the strategy that one can follow to start analyzing these functions is to try to say something about the statistics of these stationary points. And give up. So what we will do is to try to understand what is, so let's say this is strategy if you want. Well, look at the typical distribution of these special points. So these points satisfy one condition, which is that if I look at the gradient of the function on the surface of the sphere at this point, let me call it S star is equal to 0. Absolutely. Yes. Well, you will see that for this problem here, of optimization of this type of quadratic landscapes. In fact, you are in such a situation where here you basically have, so if you really want to reach the ground state, you have a special number which is 2/3, and this is related to universality. It's related, so I will go back to this. It's related to properties of the largest eigenvalue of matrices of the GOE type. So yes. Yes, maybe I'll, okay, now I will introduce a Lagrange multiplier, and I hope it will be clear, but okay, wait for that. I know it's not so much clear at the moment, but what I mean is that, so let's say, I want to use this notation for the whole gradient in the whole space. So this will be as components, which are derivative of my function with respect to Si. So this is in R to the n, if you want. But then you have to impose, so you're not interested in variation of this function in the radial direction because you are projecting on the sphere. So this object here is essentially the gradient projected on the tangent plane, if you want, so on the sphere, restricting the function to the sphere. So you want this typical distribution. You also want to understand their properties. So we spoke about, so you want the distribution as a function of the energy of these points, or the energy density. which is just the energy normalized to n. Then in general, if you think about dynamics, so stationary points can be minima, but can also be saddles. And saddles are less dangerous than minima if you think about dynamics, because saddles are points where, if you look around you, you see that the landscape in some directions is positive in curvature, so you have to climb up, but you find directions where the landscape goes down. So in principle, the gradient is able to allow you to escape from those points. So when you classify all these points, you also want to track what is their stability. Or the curvature of the landscape around you. So what does one look at to get information on curvature? Exactly, so you have to look at so if you have just one function in one dimension, you would look at second derivatives. Here you have many directions, so you have to look at the matrix of all second derivatives, which is the Hessian. Which, with the same idea of restricting on the sphere, I will call, so this is a notation which is not very appreciated by mathematicians, but I will call it like this, the Hessian matrix. So if I give you the Hessian matrix, to find the curvature, what you have to do is essentially to diagonalize this matrix and look at the eigenvalues. And to define the stability, let me introduce one quantity that is the index of a stationary point, that is just the number of negative eigenvalues of the Hessian. And this, I call this the index. So the idea is that if you have a minimum, you want this quantity to be 0, meaning that all the eigenvalues are positive, so you have a curvature like this. And then for this problem, property number 3 is what I call the geometry. So when you count these points, you also want to understand what is their overlap with your special direction, which is given by the signal V. Okay, so this is the idea next. So the idea is we look at these landscapes and we try to compute how many points satisfying this condition we find that I have this particular energy or one particular overlap with the signal, or which are minima versus saddles of a given index. Now there is a word here which is typical. So what I mean here is that, of course, you have a random landscape. So the number of points which satisfy this condition is a random variable. You change the landscape, you will have a different number. But we are thinking about large n. So what we want to actually do is to understand what happens with, if we want, a probability that goes to 1 when n goes to infinity. And this is what I will call typical in the following. So if you are at finite n, you generate your landscape many, many times. You may find a fraction of realizations where you have, I don't know, an extremely large number of stationary points of a given energy, but you're not really, maybe this happens with probability that is very small in n, and you're not really interested in that. So you're interested in what happens for most of the experiments that you do in this limit of large n. Okay, is this okay? Okay, so now with these questions in mind, we can go back to our quadratic landscape. and set up the calculation, and now I will. So we started from matrices in the inference problem, then we mapped it into a landscape, and then I want to tell you that essentially we can go back to matrices, so that all these questions about the landscape actually become, in this particular case, questions about the random matrix M. Okay. Okay, so now we go from landscape back to matrices. So did I erase the landscape? Yes. No? Yes, I did. Okay, so the function was this. Jij, Sisj, minus r over 2n, v dot Sn to the power 2. Okay, so now I want to find an equation for the stationary points, which means I take the derivative of this function with respect to all the components S. But I have this issue of implementing the spherical constraint. So I want that my function is restricted in the region of space where the norm of S square is equal to n. So one way to do this is to do this constraint optimization by adding some Lagrange multipliers. So I add an extra constant lambda, which multiplies my constraint. And I optimize this function with the Lagrange multiplier, which means that I'm looking for points which are now pairs. So I have my n-dimensional vector S and also the associated value of lambda, which I call lambda star, such that the derivative of this with respect to S and with respect to lambda is equal to 0. So if I take the derivative with respect to S, each Si, I will have the first term where I get basically twice, which cancels these two, so it remains sum over Ij, Jij, Sj. Then the derivative of the signal is minus r n v dot s over n, and then I am left with the vi over n. So maybe I can erase this. No, let me leave it. And then I have the term with the Lagrange multiplier, which gives me lambda Si. And this, when I compute it at S star lambda star, has to be equal to 0 for all I. Then I have to take the derivative with respect to lambda, and if I do it, I just get the constraint that I have to satisfy, which is some Si square minus n at S star lambda star has to be 0. At any point, actually, but in particular at stationary points. So this is equation 1, and this is equation 2. I stop in 2 minutes. So let's look at this equation, in particular equation 1. So equation 1 is a property that is not surprising, that if we derive a quadratic landscape, we have a linear equation. So this is a linear equation. And it is an equation that I can cast in this form. So if I remember that J plus BV transpose is your original matrix, so this equation can be written in the form M dot S star equals to lambda star S star, where now this is a matrix, this is a vector, so this is true for all components. I'm just rewriting this. So what's this? Eigenvalue equation. So this already tells you that if you have the eigenvalues of your matrix M, now I'm reasoning at M fixed, and you have the associated eigenvectors, which I call U alpha, from alpha going from 1 to n, which I normalize to 1. Then you have your stationary points. So then you have the points which satisfy this equation. So then S alpha, which is in relation with U alpha, so I have to put something here. Not listening to you. Good. I have to put something else here. And the hint is that I'm looking at a function which is quadratic, so it has a symmetry. Exactly. Whereas the eigenvector, so plus and minus one eigenvector is the same eigenvector. So they are defined up to the phase, but here these are two different points on the sphere, so I have to take both. So then if I have the eigenvector, these are stationary points. I add one thing. So you have the vectors, but then you have also to try to understand what are these properties, so stability, energy, and so on. So the energy is encoded in these equations. And in particular, when you want to take this equation and implement the constraint that you have, the spherical constraint. So the way you can do this is you look at this derivative here, and then you see that, for example, here you have Si, and you know what is the sum of Si squared. So one good idea is to remultiply this equation by Si and then sum over I, and then plug this expression here. So if you do this, so now let me write M as M, you get something like minus sum over Ij, Mij, Sisj, which is this plus this, plus lambda sum over I Si squared, which is equal to n. So this tells you that lambda is equal to the quadratic form Mij Sisj divided by n. And this, so if you go back to the expression of the energy, you realize that up to the minus and the 2, this is precisely the energy at the configuration S. So all of this has to be true at S star. So lambda star is equal to this, which is minus twice the energy at S star divided by n, and this is the energy density. And lambda star, so lambda star is minus twice the energy density at the point, but lambda star, if you take the stationary points labeled by alpha, was the associated eigenvalues. So if you solve the eigenvalue problem, you have for free the energy density of the stationary point, which is minus lambda alpha divided by 2. Should I stop? Okay. And stability, we do it later.